engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the programme where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith. Coming up, the WHO declare a public health emergency of international concern over the spread of monkeypox, Mpox, in Africa. So, what is the threat? Also, scientists use a laser to unlock the secret of the origin of Stonehenge's famous altar stone, and the researchers who think that horses might be far cleverer than we've previously given them credit for.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
We begin this week with a major announcement from the World Health Organization, which has declared an international public health emergency over an accelerating outbreak of a new variant, or clade, of monkeypox, or Mpox, in Africa. The viral infection, which is a close relative of smallpox and causes a painful blistering rash, swollen glands and high fevers, has been gathering momentum in Central Africa, chiefly in the Democratic Republic of the Congo. Alarmingly, this new clade, which seems to spread more efficiently, also has up to a 10% mortality rate, which is 20 times higher than the variant that caused an international outbreak 2 years ago. It's already spread to neighbouring African countries, and Sweden announced that they'd picked up a case in a returning traveller this week. I spoke to Maria van Kerkhove, who's Director of Emerging Infection at the World Health Organization, to ask her how she sees the situation evolving.
So the situation with Mpox, we're seeing an upsurge in cases across Africa, and in particular in DRC and some neighboring countries. The concern that we have is that we have this new clade called clade 1b, which we know is more severe than clade 2, which was responsible for the global outbreak that occurred between 2022 and 2023, which was brought under control in many parts of the world. This clade 1b is more severe. And we have seen a rapid increase in cases in Eastern DRC. We've seen different modes of transmission, primarily through sexual contact, and we know that this virus is circulating in sexual networks. And it requires a really comprehensive, precise response to bring that under control. Our Director General declared a public health emergency of international concern, which is the highest alarm that we have over this upsurge in cases of Mpox.
In policy terms, what does that declaration mean? What action does that translate into on the part of countries around the world?
Well, what it does is that it triggers our member states, all countries of the world, to really escalate their attention to this and escalate their response. Mpox is very different than COVID. The way that Mpox is transmitting is this contact-to-contact, physical contact. And what is alarming is around the sexual contact that we've seen. And once this virus gets into sexual networks, it's difficult to control, but it can be controlled. And I think what we need from our member states, from countries, is to really focus on, first of all, understanding the epidemiology, what's actually happening on the ground, increase surveillance, support patients who have Mpox, make sure that we do contact tracing so we could prevent the onward spread through risk communication, through targeted measures in at-risk groups, working with our civil society partners, working with non-governmental organizations, working with local partners to make sure those messages that are actually out there to prevent the onward spread. And we also want to see governments work together to use medical countermeasures like diagnostics, therapeutics, vaccines in a targeted way, preventing spread, preventing deaths in the most at-risk groups in these key countries.
What's our vaccine capacity like? Because when this came along in 2022, obviously different clade, but the same vaccines are going to work. There was a problem initially with scale-up. Has that been solved, or are we still facing a shortfall of vaccine?
We're still facing challenges on the vaccine front, but I do want to emphasize that vaccines are one intervention. There are so many other interventions that we can additionally use, like I mentioned before, related to the risk communication materials. We saw mainly this clade 2 outbreak, this global outbreak, be brought under control through communities through risk communication and preventative measures. Vaccines were very helpful, but vaccines weren't really what brought it under control. In the current situation, which is driven by this clade 1b, we will use vaccination as part of the response, but we do see some challenges in terms of supply. We are working through our medical countermeasures group to be able to pull together partners, manufacturers, countries that have vaccines that want to donate those vaccines, or working with manufacturers on the supply to be able to pull that together to understand the numbers of vaccines that are available, when they expire, how we can set up an allocation mechanism based on risk and need to really deal with equity here. But it is a challenge.
Is the World Health Organization, therefore, by its response, concerned that we are going to see effectively outbreaks in other satellite parts of the world that are connected by travel to this place in Africa? We've already got a case in Sweden being declared now. That's good. It shows the system is working. It's being picked up. But is that the main worry here, that we're going to see this almost endemicizing elsewhere around the world if this gets away from us?
The main concern we have is in Africa. And what we are seeing is certainly an escalation and an upsurge, an expanding outbreak. These viruses don't respect borders. They travel in people. And there's a lot that we can do to focus the support on individuals to make sure that they have the right information to protect themselves from getting infected. That's one of the key things we need to do right now, is to ensure that people have accurate information. They know where to get care, they know how to get tested, and they know how to prevent the onward spread. Certainly, we could see cases popping up in other parts of the world, but as you said, this is showing that the surveillance system is in place. There's no reason why this clade 1 would become endemic in other parts of the world. What we really need to do is put the resources at the source, support the countries in doing what they are, so that this expanding outbreak can start to retract. And we can do that through a combination of effective measures.
The WHO's Maria van Kerkhove there. Some commentators are actually predicting that it will only be a matter of time before the UK detects cases here too. We'll keep you posted. Stonehenge, the 5,000-year-old stone circle on England's Salisbury Plain, was constructed using a mixture of local and imported rocks. Archaeologists had matched some of the keystones to volcanic deposits in neighbouring Wales, while others come from Salisbury itself. But one rock, the enormous sandstone altar stone at the centre, is different. It isn't local stone, and it isn't Welsh. So where had it come from? Well, now, using a new analytical technique involving dissecting the rock grain by grain with a laser to understand its chemical profile, scientists at Western Australia's Curtin University have come to the surprising conclusion that this key part of the structure has actually travelled a considerable distance to get to the centre of Stonehenge. PhD student Anthony Clark is the lead author on the new study.
The people at Stonehenge didn't leave any written record, so we have to turn to the rocks or the megaliths themselves to understand their culture and motives and the history of prehistoric Britain. Stonehenge is actually made up of different kinds of rocks. The large upright sarsen stones are from the local area near Stonehenge on the Salisbury Plain. The inner ring of upright bluestones are from West Wales in the Preseli Mountains. That leaves the central rock called the altar stone. Previous work thought it might have come from Wales in the Brecon Beacons, but the ultimate origin was unknown. So it was the kind of last remaining question in the Stonehenge story.
How do we know that the different stones came from the different areas? What tells us that they have different geographical origins?
The large sarsens have a distinct chemistry that has been matched to rocks that are lying on the surface of the Salisbury Plain. The bluestones are igneous rocks, which means they formed from cooling and freezing magma deep beneath the Earth's surface. That allows us to figure out their age because we can figure out when this crystallizing process happened. And when we do that, we can figure out that they're from these particular mountains in West Wales. But the altar stone is a bit different. It's a sandstone, which means it's made up of squished together sand, much like sand on the beach. Now, that means that the altar stone doesn't have one true age per se. It's lots of different grains of lots of different ages and chemical characteristics all squished together. So figuring out the age of the altar stone is a bit more tricky compared to the other rocks at Stonehenge.
How have you done it then?
So if we analyze the altar stone, now, of course, we can't just go up to the altar stone and smash off a bit with a hammer, but we have samples collected from the altar stone during previous archaeological digs in the early 20th century. And very thin slices of rock have been prepared from these samples. And we can look at them under the microscope, and we can also hit them with a very microscopic laser, the width of a human hair. And when we hit these grains within the altar stone, it ablates a very, very small portion of that grain. We can then analyze this gas that comes off from these grains and analyze its chemical and thus isotopic characteristics. Now, isotopes let you figure out the age at which that tiny grain or mineral crystallized, much like the bigger rocks at Stonehenge, the bluestones, but we're doing it on a grain by grain kind of scale.
But how do you then map that to where it came from? So that gives you a sort of chemical and a structural fingerprint for that stone. How do you
That's
then
right.
take that away and say, right, I think it came from wherever?
Yeah, that's right. You build up this profile, this fingerprint. It's like a DNA sequence for a rock. So you can kind of figure out the parent rocks, the mountain ranges that were eroding and shedding their unique age and chemical characteristics into the rock that would eventually become the altar stone. So once we build up this fingerprint of the altar stone, we can just simply compare it to rocks throughout Britain, Ireland, and Northern Europe. And when we did that, it really was so distinctly Scottish. It helped us match to the Orcadian Basin of northeast Scotland, which is about 700 kilometres away from Stonehenge.
But that still means that someone thousands of years ago, a group, transported then something weighing a huge amount, hundreds of kilometres. Why would they pick on that particular rock? Is there any kind of insight into why they liked that rock and brought it all that way?
That's the really fascinating, perhaps unanswerable question in this story. If you look at the altar stone, I was there yesterday looking at the rock. It's this rather ordinary looking green grey sandstone that's kind of partially buried in the earth. I wouldn't personally transport it over 700 kilometers away from Scotland, but rocks have always fascinated humans. We've always sought the perfect stone for our construction. Today, millionaires will adorn their bathrooms with Calcutta marble from Italy. I don't understand why they do that. And perhaps the average Neolithic Briton felt the same way about the altar stone.
Oh, I might get rid of my bathroom tiles then. But more seriously, Anthony, is there any other geological process that could have brought that stone to a nearer venue, and so they only had to transport it less far? Perhaps, I mean, we know there were ice sheets and various glacial processes. Could it have got there by chance, and then they just thought, well, that's a handy stone, and moved it from the near neighbourhood?
Yeah, that would have been very convenient for Neolithic Britons if vast sheets of ice had conveniently delivered it to the Salisbury Plain. But if we look at glacial reconstructions during the previous million years or so, when the United Kingdom was a frozen tundra, ice was actually flowing northwards from the vast mountains of Scotland, and it was flowing northward, taking material away from the Salisbury Plain. So it really doesn't look like a natural process carried the altar stone. There's also no evidence of glacial movement in the Salisbury Plain, nor on the altar stone itself. We don't see any scratches of ice. We don't see evidence of it being carted 700 kilometers away in an ice.
You began by saying that the people who built Stonehenge left us no written record. I suppose their writing is their creation of this interesting structure. What can we infer then, or deduce about them, what they knew, what technologies they had, based on what you've now shown about the origin of this stone?
Again, yeah, these are really fascinating questions, and it's going to really help us reconsider the connectivity of Neolithic Britain, given that we have these two population centres on the Salisbury Plain, and then, of course, up in Orkney, which has some really famous Neolithic monuments, Skara Brae, the Ring of Brodgar. Were these two population centres connected? For many archaeologists, Orkney, northeast Scotland, was a centre of trade, population, and farming. There is also evidence that points towards Neolithic Britons having quite capable shipping technology. We find evidence of amber and pottery and axe heads all throughout the North Sea area that must have been delivered to these islands on boat. There's evidence of cattle being moved to Orkney. So if they're able to move substantial cattle, perhaps the author's zone was part and parcel.
Anthony Clark there, and that work has just been published in the journal Nature.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith. Still to come, don't frighten the horses, why our equine friends are far smarter, it turns out, than we thought previously. But first, scientists in the United States have discovered a reservoir of liquid water on Mars. It follows the analysis of data from Mars's InSight lander, which touched down on the planet in 2018 and began to analyse Marsquakes, the Martian equivalent of earthquakes, using the vibrations to unpick what's actually going on beneath the surface of Mars. I've been speaking to Michael Manger, who's at the University of California, Berkeley, beginning by asking him where the water that is on Mars might have come from.
So Mars was wet, at least episodically, 3-4 billion years ago. And so much of the drying happened over the last 3 billion years. Where did water on the rocky planets come from? It's still the subject of active debate and controversy. Even for the Earth, we don't know where our water came from. But presumably Mars's water came from the same place, some of it when it first formed, and some from comets later on in its history. But deciphering that question is a really tough one.
So why do you think, or what sort of hypotheses have you got for where it went? Because if it had similar amounts of water to the Earth, which is not an unreasonable supposition, is it? Why have we got so much and Mars is now a prune of a planet, relatively speaking?
Well, our conclusion is, in fact, that Mars may actually have as much liquid water in proportion to its size as the Earth. If we look at the surface of Mars right now, there's a large ice sheet at the North and South Pole. And we conclude that there's probably 1 to 2 kilometers depth of water in the mid-crust of Mars. So not a dry planet by any means.
How have you been trying to get to the bottom of this, or sort of scratch beneath the surface to see where all this water is, and if you're right, that there's ice and water within the substance of the surface of the planet?
Looking deep is difficult because we can't use light, but we can use other types of waves. When Marsquakes happened, they shake the ground, and the InSight lander had an instrument called a seismometer that measures vibrations of the ground. And the speed at which those seismic waves, those vibrations travel, depends on the properties of the material the waves are traveling through. So the composition of the rock, whether the rocks are full of fractures, and then what's sitting inside those fractures. And we find that they're best explained by having a crust full of cracks and then filling those cracks with liquid water.
What temperature would it be at then, do you estimate?
We're talking about depths of about 10 kilometers to 20 kilometers. And so at those high pressures, the boiling temperature of water is higher than 100 degrees Celsius. And I'm guessing that we're basically seeing temperatures from the top of the water that are about 100 degrees Celsius down to maybe 200 degrees Celsius at the bottom of the water.
Was the water always there like that then, or has it retreated inside the planet at some point in its life?
If we think about how the water cycle on Earth works, we see water continually being exchanged between the atmosphere, the oceans, what we call groundwater, water that sits inside the crust, then water in lakes, rivers, and streams. Water is continually being transferred between these different areas. There's no reason to think Mars was much different. And what we're seeing now is just the leftover of that groundwater.
Do you think then the rest of it has boiled off or been lost into space, for example?
For sure, some has been lost to space. And we know that by measuring isotopes of the element hydrogen in both rocks excavated by impacts, meteorites, as well as the atmosphere. But the amount of water that would have been lost is very small compared to how much water we think we're seeing.
Now, if there is liquid water there, that obviously has a lot of implications, both geologically, but also biologically. If there was at some point, or still is, life processes happening on Mars. So if the water's retreated into the crust, is it possible that life processes, life, could have retreated there with it, and therefore could it still be in existence in there somewhere?
So I want to make clear, of course, that we have not found any evidence for life, nor have we established that water is a habitable environment. But at least on the Earth, where we see water, deep underground, we also see microbial life. So if there was once life on Mars and the subsurface is habitable, meaning there's also an energy source, then this could be one of the settings in which we might want to look for life.
When you say an energy source, what sorts of things could power life down at those sorts of depths?
So one possibility would be gases such as methane that can be produced by geochemical reactions or hydrogen gas. These are some of the energy sources that microbial communities on Earth take advantage of underground. Deep underground, you don't have access to light, so photosynthesis is not a great way to get energy.
We have seen also extreme bacteria deep underground found in mines under South Africa, for example, that were thriving on radiation,
Correct.
uranium in the rocks. Is that a possible model on Mars as well?
I don't see any reason why not. We think the rocks on Mars are not that different from the rocks on the Earth. And you're absolutely right. When we go deep underground and deep mines in South Africa and Canada, we do find evidence for life, microbial life.
So how are you going to take this forward then? You've got these observations. They seem to fit with the explanation that there is deep liquid water. It's at high temperature down there, but you've got all this water down there. What are you going to do next to sort of flush out how this got there, whether it really is there, and what it's doing?
So one of the puzzles was that as we go to more shallow depths, the crust gets colder and the liquid water would be frozen as ice. And so we did try and use the seismic data to look for evidence for this ice, and we don't see it. So I'm quite curious why there's no ice sitting on top of this water. I think the next step is to try and understand better the history of this water, how it connects to the surface environments, and how Mars could have evolved to a state that we see. I'm sure there's much to be learned from continued analysis of that data.
Michael Manger from the University of California, Berkeley. New research suggests that horses might be considerably smarter than we previously thought. The study, which was carried out by scientists at Nottingham Trent University, found that our equine friends were cognitively one step ahead of the researchers, who were initially baffled that the animals could learn a basic reward task incredibly quickly, but then seemed to perform worse than a goldfish when the rules of the game changed. That was until they realised that the horses had actually sussed that they didn't need to cooperate in the next stage of the task, so they didn't bother. Who'd have thought it? Louise Evans carried out the study.
I trained a group of 20 horses to touch a target, which was a piece of card. And whenever the horse touched the target with their nose, they got a treat, and that motivated them to touch the target every time they saw it. To test whether they could control this impulse once they'd learnt it, I introduced a light cue. So I was wearing a cyclist's head torch, and whenever the light was on, that was the horse's cue to stop, just like a stoplight on a traffic light system. And when I switched the light back off again, they could touch the target and be rewarded with the food like normal.
And how quickly did they pick it up, or did they not pick it up at all?
Well, that's the thing, Chris. They didn't pick it up very well at all. So we trained this group of horses for 3 weeks, and all of our horses were doing really poorly, which was very concerning to us because we know that goldfish can do this.
For comparison purposes, how quickly did they learn the first task? As in, I present the target, if they come and touch it, I give them a reward.
Yes, so they picked up that task within 3 training sessions. So we were expecting them to be sort of similar with this task. And actually what we saw was that they were touching the target every single time, regardless of whether that stop light was on. We do ride horses, we sit on their backs, we put ourselves in dangerous positions with horses. So if they're not as smart as a goldfish, that is quite concerning.
Well, yeah. So what did you think was going on then? Do you think they were just being obstinate, or was there actually something about the training they just couldn't learn this?
So one of the ideas we had was maybe horses just can't do this. They're just not able to control that urge to touch the target when there's food involved. We also thought maybe they just can't see the light very well, although we did think that was unlikely because it was quite bright. And our third possible explanation, which is what we wanted to test in this study, was whether horses had maybe figured out a clever way to cheat the game or to take part in this task in a lazy way. And what I mean by that is maybe the horses had figured out that actually, if they touch the target every single time, sometimes they get rewarded and sometimes they don't get rewarded, but nothing bad ever happens. They never get punished. So why would they bother expending the sort of mental energy it takes to pay attention to a light when they could just ignore the light and touch the target every time?
So that means if you introduce some kind of bad outcome if they do it wrong, they touch the target when they shouldn't, will that motivate them more to then comply?
Well, that was exactly what we tested. So we gave the horses another 3 training sessions. And this time, when they ignored the stoplight and continued to touch the target, we gave them a 10-second penalty. I stepped away from the horse and I removed the target from their reach so they couldn't access the game.
And then what happened? Did they learn it after that?
So as soon as we introduced cost, the horses all started listening to the light cue and following the rules and playing by the rules. And what that suggested to us is that perhaps the horses had actually understood the task all along. Because if they were just learning from the introduction of that penalty, we would expect them to gradually improve their performance, whereas this was a very sudden switch in strategy that we observed.
It was more a case of who's playing with who by the sound of it, isn't it? So they actually basically had sussed you out. They knew what was going on. They knew the score. This elevates horses above goldfish, presumably. Does this mean you're seeing your horses in a totally new light now then?
Yeah, exactly. The really exciting part about this study is that we seem to have uncovered an ability that we didn't know horses could do. It's called model-based learning, but what that means is that the horse kind of builds a mental model or a mental picture of the game, of the different actions they could take and the different outcomes that they might have. And that's a really advanced skill. It's a little bit like a human playing chess. You build a mental model, a mental map of, well, if I move this piece here, then my opponent might be able to move his piece here. It's that forward thinking, a couple of steps ahead, that we didn't know horses were capable of.
Obviously, they didn't evolve this behaviour with you coming along after millions of years of evolution to play a game with them. They must have evolved this to give them some kind of competitive advantage in the wild or in their evolutionary time.
Well, that's what's really interesting about this, Chris, because horses don't really have to strategize in this way in the wild. Horses generally eat grass, which is available to them all of the time. They don't sort of need to stalk and hunt prey or search for food very often. We're not quite sure yet why horses are able to do this or what benefit it might have to them. We're really hoping that we can do some more research into this and find out that answer to your question.
Louise Evans, who conducted that research at Nottingham Trent University. Well, now it's time for Question of the Week, and my colleague James Titko has been getting to grips with this fiery question from listener John.
Hello, Naked Scientists. This is John Bondi from the U.S. Wildfires in the U.S. and Canada are big news at the moment and have been so in recent summers. How many tons of carbon are released by the wildfires, and how does that number compare to the release of greenhouse gases by other human activities like cars, heating, electrical generation, etc.? Thanks.
Thanks, John. Carbon dioxide from wildfires is a growing source of emissions globally. You're asking the question at a very pertinent time. To answer it, we got in touch with Jim Dale from British Weather Services.
Unfortunately, there can be no definitive answer to your question, John. The first thing to say is every wildfire is different. Different locations, different combustible fuel, different meteorological factors. The Canadian wildfires of last year and this were much bigger than the Athens fire of now. And even when the spread is curtailed, the underlying moss or peat can continue to quietly burn, releasing further carbon and other gases over time. The 2023 Canadian wildfire that put masses of smoke into the Great Lakes area and northeastern parts of the US was off the scale and produced as much greenhouse gas emissions in a single season as would normally occur over 10 seasons. That's according to the collated data. The Canadian fires produced about 2 billion tonnes of CO2 alone. In 2023, it is estimated that 8.6 billion tonnes of carbon dioxide was released globally through wildfires alone, near doubling the estimated 4.8 billion annual emissions of the US from all other sources. So on that comparison alone, wildfires as a result of climate change have the capacity to overhaul traditional emissions and undo all forms of man-made or even natural climate mitigation. However, in all the short-term negatives, there is a longer-term positive in that the regrowth of vegetation across burned areas takes up much of the carbon released in the fires. So, it's very much an ongoing and ever-changing situation. However, there is sound evidence that wildfires are potentially doubling the conventional carbon release of human beings worldwide. It's a worrying scenario for all the reasons given, and it's very likely to become worse within our lifetimes.
Thanks, Jim, and thanks to everyone getting involved on the forum on John's question. A good healthy debate which you can get involved with yourself over at nakedscientists.com/forum. Next week, we'll be answering this question from listener James.
Why do cobwebs feel so weird when they touch your skin? Is it something to do with the web itself, or maybe fear of spiders, or something else? Thanks.
And if you've got a question of your own, or you can help us out with an answer to that one, do get in touch. It's chris@thenakedscientist.com. And that is all we have time for this week. But on Tuesday, we will be putting cosmetic products and treatments under the microscope to ask whether some of them could put us at risk of cancer. Tattoos are on that list. Alarming, eh? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.